Okay, so I'm going to talk about the printf debugging or the printf, which is debugging, of course. So I'll talk about printf and debugging and printf debugging. And we lots of interesting anecdotes. Oh, be careful. So my IT guys installed antivirus software on my machine, and that doesn't work anymore. Yes. All right. So you have to establish your credentials with the crowd, right? So I'm showing this slide to make you all understand after this super slide. Yeah. But yeah, well, I don't know. The most important thing, I guess, is the 15 years I've been doing Erlang programming for money.
Sorry, how do you survive to experiment that nuclear physics?
Say again?
How do you survive to experiment that nuclear physics?
You have to have lead uniform on. No, it's not that difficult. I've only been irradiated once. But
I bet you're going to do well.
Yes, it was actually okay. So I'm going to tell an anecdote about that. Before I started with Ericsson, I was working in this lab in the U.S. Called Brookhaven, and so I was sitting there in the lab typing away at my computer, and three guys with actual LEDs. They had LED suits on and masks. They looked like astronauts, and they walked past me, and they were carrying this big LED box, and. So I was like, what's going on? And it's like, well, we had a mishap in the accelerator. We have to bring out all this radioactive material. And I was like, should I leave? Not a problem. Anyways, so then I started, I quit and started there. But now I work at Klarna. So I have to show this graph, of course. Marketing people help me out to tell me how to show this graph. This is the classic hockey stick. So this is where I started working at Klarna. 6 pixels, I think. Now, yeah, purchases. That's not when we buy companies. That's when people make the purchases online shop, right? And we handle the payment. So there's two interesting things here. One is that you can multiply this number by 5, and then you get the number of euros. That's our revenue. So each of these purchases gives us, on average, a €5 revenue. So that's good. And the second thing is that we're kind of having a bit of a scaling problem here. So the transaction volume has increased by a factor of 100 since I started working. So we're having some interesting problems, and among them, of course, is debugging. So this is a conclusion. Totally different talk I gave many years ago, Ericsson, and this was my conclusion. Introduce this time sort of debuggability, which is a core feature of Erlang, I think. And I was trying to talk my bosses at Ericsson into using more Erlang, but that didn't work. So that's another reason I quit there. All right. So I was started thinking about that when I saw this thing. This is a joke account on Twitter. Shit HN says. So it's like stupid quotes from Hacker News. Assume everybody knows about. Many stupid things here, but this is actually not so stupid. Printing stuff to screen is a program's best debugging. Yeah, well. It's actually sad but true. There is many ways to debug it. Many, but several ways. But you can do all these things. But if you're working in a real-time system, or if in a production system, especially if it's real-time, there's really no way to do sensible debugging without printf debugging, which is you instrument your code to write stuff on the screen when some particular thing happens. Of course, has some problems too. For example, you have to edit and refile your code, so that can be tricky. You can include bugs. In the embedded system, you might not even have a compiler. Your boss might not want you to put shit in the code base on a Lite server. Yeah, it kind of sucks all around. Of course, since we're using Erlang, we have the silver bullet pricing. So it does all these things. It's actually pretty excellent. So, probably got my slides wrong over that. But basically what tracing is about is that you can, on the fly, instrument your code with debug code. And in Erlang, that's done with something called a trace. It's someone per process, and you have some different types of tracing you can do. The most interesting ones for debugging is the message passing tracing. So when you have these actors, Erlang processes that send messages to each other, you can instrument the emulator to give you an event every time a message is sent or received. And the call tracing, which is you instrument your code once it's loaded in the emulator, you can instrument it to give you messages when certain things happen. You can also instrument the garbage collector and the scheduler, but that's more interesting for profilers. And there's other stuff too, but these are the most important ones. So, and every time you trigger something, by default, you have to set up an Erlang process, and that process will get this event, that message that the tracer generates. Or you can write it in file. I've never given this talk before, so I'm not sure what's going to show up. Right, I don't know if you can see this, but I'm going to try to show some code here. Where's something to point with? I'm so old-fashioned now that they have a danger. Look at this. Oh. I've used the wrong right color. Alright, so I'm setting up an environment here. I self here. Now it's getting a bit Erlang here, but self is a function that gives you back the P, your own P. So here we're working in the Erlang shell. It's a REPL for Erlang. And the shell itself is, of course, a process. So I'm getting the shell here is a variable, and now it holds the P of the shell. And then I write the function here, and then I'm going to, well, it used to be harmless, but we bind it to F here. I start to set the tracer on the shell process and the running flag, which means the schedule. So I'm telling the emulator to give me an event every time this process is scheduled. And then I tell, so I wait for 3 seconds, and then I send the message queue to the shell. Ooh. Okay. Hopefully, at least some of you understood anything of that. So basically, I make a function that starts the tracing, so we get all these messages, wait for 3 seconds, and I send back to shell so I can see it. And then I spawn this function. Okay. All right. So once I do the spawn here, nothing will happen. But after 3 seconds, this process will die. This process I spawn here will die and send it up to the shell. So here I wait for 3 seconds and then I flush so I can see the messages. And what do you know? We got a bunch of messages here, trace messages. This is the PID channel. It's scheduled out 3 times. It's scheduled in once. Yeah. This is pretty cool. This is actually pretty excellent. But my explanation wasn't very good. But how does this help us? We want to print that, right? Not some stupid scheduler. But so we need to instrument an operator function without recompile. How hard could it be? Well, it's not very hard at all. If there's a function that does that. Trace pattern. So you tell this function as MFA, the module functionality of the function you want to trace on, and then it you can wild call it, so this will instrument every function in lists module. Okay, and then you have to have some code that does something that you can't just tell which function you want to trace on, you have to tell what you want to do if you want. So, and that's done with something called match specs. It's a small language, it's very, very cryptic. And the match spec has a head, a condition, and a body. So it's like the head, like the function has no line. You can set up a match on the coordinates that the function is called. The condition, which is like a guard, and there's a body that tells you what to do. Let's look at an example. Yeah, here's the part of the specification of this match spec language. At least I think that's pretty cryptic, but maybe not for you, eggheads. But here's an example. So, say I want to have my problem is I'm trying to do something on a function, on a trace on a function, but only the functions have 2 arguments, and I'm only interested in events when they're equal to each other with 2 arguments. And the head of the argument is less than 2. Okay, so then I set up this. So the first bit here is the same. I want 2 arguments. They should be the same. So that's what's matching here. It says $1 is. I want to find the variable there, $1, and the 2 arguments should be equal. And now I want it to be less than head to head. The argument there should be less than 3. Obviously. Yeah, maybe. Alright, so now I'm trying to do my shell example again. It's the same as previous, except I find this match spec variable here and the MFA. So I want to trace in this function at least 10, but only if the 2 arguments are equal and greater than 3. And then I do this fun trick that I showed you before. So I find this variable f here to this fun that does this. So now I call them both trace and trace path. Okay. Alright, so I spawn away my tracer, and then I call this pen twice. The arguments are identical, not identical. And then I wait 3 seconds, look at it. So I only got 1 message when this append was called with the 2, because the head of the argument is supposed to be less than 3. So ignore this, because it didn't meet the match condition. And this is actually awesomely cool, because one problem with all other kinds of debugging is that often it's only when something special happens. So you have a function that's called a million times a second, but sometimes it's called by some particular argument, 0, for example. Then everything goes bad. You're only interested in those. So this is pretty cool. All right, so it's cool, it's wonderful, how does it work? I'm not gonna read this to you. I'm assuming you can all read, but basically it's done by the loader. The loader will put a no operation in, there's a beam instruction called no. We'll put that into various places in the beam code and it's loaded into the emulator. And that no can be turned into a jump, basically, by the trace function. So here's the world's worst picture. Yeah. So this is supposed to be a piece of beam code that's loaded into the emulator, and there's a bunch of instructions, blah, 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 and the program counter is moving down like this. So this is entry to our function, and then there's a no, and then it does all this stuff. That's normal, the way it normally works. And so to execute that no is, of course, very, very cheap, so it doesn't really impact the program. When you set up tracing on this function here, you change the no into a jump, or whatever it's called. It's not called a jump, I don't know. That jump jumps you to this bit of code, which is that match spec thing. I guess it's only to some code where it's running some special little emulator. So it runs that stuff, the match spec code, and then jumps back in. So the cost of the tracing is very low, unless you're actually using it. Alright, cool. Alright, so I'm going to tell the war story again. There was some bad pictures, there was code, stolen code, walls of text. I'm going to do a war story here. All the bad things you can do in the presentation. So this is when I was working at Ericsson. It's like 98 probably. So the emulator the system we had was using OTR5, which was the first version of Erlang that had some trace functionality. So it was solver was Lite in Denmark taking traffic. Of course, since it was deployed at the operator's facilities, there was no way to get to it. You couldn't hack it. The phone companies don't like machines that are accessible. I couldn't load no code, there wasn't any tools. The only way to get to it was to write to it and hook up a terminal to it, or a PC or something. And the problem was that every 3 months, the load on this machine was pretty low, but after 90 days, the load became very high and the node became unstable. So it's like phone companies do, they sent a guy out there 89 days and rebooted the machine. So this would never happen. But they were unhappy with this, especially if they had many machines, many servers like this. They would have to have a guy that did nothing else, which is, of course, not so unusual for operators. But anyways, so I was asked to fix this, and so I wrote a line of Erlang code, and I would run a trace for 1 minute and then write the results of a file. So it's very similar to the program that's shown here. Set up a tracer in the shell. Then I mailed this Danish guy this one-liner. And so he drove out to the machine, so he waited 91 days instead. So we got into this bad situation, and he ran my code, and then rebooted and ran it one more time, and then the email was 2,000. This is pretty high latency debugging, but so then I have these two files, one when the system was happy and one when the system was unhappy. So then I could write a small profiler and compared the execution time for each function in the system before and after. It turned out that it was a function called xlookup. It became like 100 times slower after 90 days. And that was because the hash function. So once there was ets is a dictionary, a built-in dictionary function. So it hashes the keys, and there was this one table that had integers as a key, but once the integers got too big, the hash function stopped working, so it hashed everything to the same bucket. And so all our data wound up in one bucket in the dictionary. It became super slow. And the point of this, of course, is that I don't think there's any way we could have found this problem without this tracing. This is pretty cool. Another war story. Boring. This was the famous Frankfurt incident that Sultan here is well aware of. We had a customer in Germany. They had a bunch of AXDs, AXD31, famous Ericsson Erlang switch. There's a famous Ericsson switch implemented in Erlang. And this machine had big problems. I would restart and hang and all kinds of stuff. And of course, since this was pretty difficult task, they sent it to Budapest. I was working here at whatever it's called, even your shift, no?
What is science for?
The science part. Yes, and we were doing fourth line support or whatever it's called. So we were supposed to find out what was going on with this stupid switch. Yeah, so it wasn't in Denmark, it was in Germany, and this switch had, as I understand it, millions of people connected. It was a German phone company, and it had like 8 or so switches. So it was 1/8 of the German, their customers. Probably is. But 10,000 ongoing calls. There was still no debugging support in our time. Well, there was, but nothing was helpful here because we didn't really know what was going on. It was just behaving very badly. I did have shell access this time, so I could log on to it and get a shell. So I wrote this. Since I didn't have an editor, I couldn't load code. I only had a shell. So I had to write stuff in the shell. I wrote this. This is one line, but of course that's just a technicality. But it's a built-out version of that code I showed earlier. And you can see it uses trace pattern and trace here and there. That's actually the thing that's on my t-shirt. That's why I'm wearing this ill-fitting t-shirt. So Erlang Solutions made a t-shirt about this code. Evil people. I should have cooperated. Yes, I did get that. So, but that's okay. They didn't call us. They called eventually when they were calling it, they called it. But it turned out to be hardware. I don't think we ever really found out what the problem was, but they switched out some call in the switch, and then the problem arose. So it was the switch balls, I think. But the other outcome was that, so this tracing is great, obviously, but it's way too complicated. You can't write one-liners like that all the time. There is of course, a layer in OTP or a tool in OTP that uses this and tries to make it more user-friendly, but it's still way too complicated. And the reason I didn't use this DBG thing in the German switch was that several times I crashed the machines in our test lab. It allows you to set up traces that would kill them, or at least it did then. So I created something called Redbug, which was basically that one-liner that's now expanded into 1,000 lines of code. So what I wanted was something that looked like this, a function that I could call that would take something that looks like Erlang options. Blah, blah, blah. So I wanted to be able to do something like this. If I wanted to trace on this append exec when the two arguments are equal and they're big less than 3. So that's what I wanted to do earlier. I had to write this what I think is pretty complicated match thing. This is what I wanted. And that's what Redbug does. So basically only one function. It's Redbug stored, and then you put in a string like this, scratch the trace, and there you go. You can do guards, like that. Yeah, like this. So here, this is basically the same example. It is exactly the same example as all. So I set up a trace on this append, x with the two arguments are equal, greater than 3. I call it 3 times. I'll only go for 1 hit, which is what it's supposed to do. And then the Redbug times out by itself. It has one other killer feature, I think, it's the stack thing. So in a big system like the HP381, there was often you have problems in a function that would crash, perhaps to do something bad with the database. But it did something bad because it was called with a bad argument. But you didn't know who called it. So if you have this function, it can get called from 100 different places. Who is it that calls the function with a bad argument? That's a question I found myself asking many times. So I implement this stack thing here. So it's the same trace again, except this time I want to see the stack when it triggered. And it looks like this instead. I get this, called this append with a 2 argument here. But here, now I can see where it came from, and this is the shell. So, it's called from here. This is actually great, and something you should use all the time. It has one other action, that's the return value. So obviously, sometimes you want to see the return value of the code. So, go this append again here. We want to see the return value. And now when I run this, it tells me that I call this append, and then it tells me that this append is on this. This is also something that's super valuable in a big system. In the shell, I mean, obviously you see the answer here as well. This one is the same as this one, but if you're in a big system, it doesn't work. Yeah. So this is the manual. Alright. So Redbug has some, also the safety of this is that it will always turn itself off. You can't make it go for, well, you can, but it's not supposed to do. So either it turns itself off after some time, like 15 seconds in default, if you stop the trace and it will turn itself off after 15 seconds. Or after 10 messages in this case. It will also kill itself if it gets into trouble, if there's too many messages coming in, too big messages or blah blah blah. So it's pretty consultative. I can say we run it all the time at Klarna or work. We run this to live machines all the time, and it's never a crashed machine. So it's better than the Frankfurt one. Yeah, you can specify which processes you want to trace on, and also it's distributed, of course, so you can trace on a different node, which can be useful. You might not have access to all the nodes by all means. Yeah, some other options. And this one is a bit interesting. So you can tell the emulator when you set up a trace, normally, like I said, the trace messages go from all processes, local or distributed. But you can also, the emulator can write the trace messages straight to file, so it doesn't have to turn them into terms and move them up to all space. So directly from the emulator, it just writes into file, which normally has a lot lower impact on the system. So if you want to do profiling, that's the way to go. so it has some support for that. Oh, okay. I guess I'm done. Google thinks I'm done. Second.
Eventually exactly on time. So
Exactly on time.
you can remember it's 2 questions.
Yeah, it's kind of interesting that not much has changed. That I'm still responsible for one live system. It's pretty big, and it's always sending one-liners to customers. If the problem wants to kind of improve something, probably it's point A.
It's actually shipped to the reader.
Yeah.
So, but yeah, I don't know. And I don't know. I don't feel like. I mean, I like Redbug, of course, but I'm not trying to sell it. I want. But I do want to feel like I want to inform people that the tracing exists. It is super powerful, and then it's annoying to me that DBG is so bad. He should make something that much better.
It really sucks.
It does. And it's, I mean, this is probably not optional either, but it's much better. And it could have been even better. Maybe if I give this talk enough times, those people get their butts into gear and write something.
I don't know about Redbug when I was doing something. I had a problem when I was at Motorola, where I had a C program that didn't work. They assigned me to C stuff, all these stupid things that you do in Erlang. And I had to reload the program in Erlang to simulate it, and then do all these tracing, so I could figure out what was wrong with the C program. And I found 4 bugs in it using these tracing things, which was awesome. So it's a wonderful tool, this tracing. It takes a little bit of used to, as you say, much, but it's once you get into it, it's wonderful. I'll try Redbug now because it looks more safe. But you do lose a few hair every time you write one of those.
If you want to make a complicated match stack, I mean, this was a pretty trivial example I wrote there, and we still, what the fuck?
Yeah.
Yeah.
Max, can you use this for tracing from an outside Erlang node without deploying the Redbug on the target node?
Yeah, it actually has a feature that it doesn't have to be available to the machine that you want to trace on, because it loads itself over the Erlang distribution. So the first thing it does is it checks if the target machine has the latest version of Redbug, and if it doesn't, it'll load itself from the machine where I'm tracing. That's actually something I had to do because of where the lab was set up in Hungary. But that's a valuable feature. So that I can actually start the Redbug trace from Bash. So there's a script there that run Redbug from Bash and starts a machine, hooks up to the green machine, runs the trace, and goes back to Bash, which is worthless feature, but yeah.
Can we somehow turn this tracing entirely off from the system? Because I suspect some remote code execution issue. Changing this no operator to jump undetectable.
This is all done by the loader will lay it out like that with the note there. That's not something that we do. That's when you load the bean code into the machine, it always does that.
So if you want to secure your Erlang node, then you use a cookie, and in principle, if you don't have that cookie, you can't connect anyway. And if you do have a cookie, you can run Redbug.
Yeah.
And then you can do anything else.
That's great. Yeah, and the only thing it can do that, I mean, you can't change the jump thing to do arbitrary code execution. It has to, you can only point to one of these match things. And they can do only very limited number of things. It's not a real language to match that. Although it's complicated, more complicated than many real languages.